Good afternoon. We have one speaker in this session, and I invite Professor P.P. Pradyumnan to chair this session. Please.
Okay, thank you, Professor Vinod. And also, thank you very much, Professor Jim Jose, for accepting our invitation for giving this webinar. Okay, first of all, and good morning and good afternoon, dear friends. Good morning, Professor Jim Jose. And Professor Jim Jose is really is a good friend of mine during my research at MG University, Kottayam. And while I am coming from there to here, he was just joined as a researcher in Mahatma Gandhi University, Kottayam. And that's why he's a very good friend of mine. And Professor Jim Jose received, now I am giving an introduction to Professor Jim Jose. Professor Jim Jose received his MSc from University of Calicut and PhD from Mahatma Gandhi University, Kottayam. And then he joined, he done PDF. He was a research fellow at, hello? Can you hear? He was a research fellow at the Department of Di Fisica, Milano, Italy during 2001 to 2002. He was senior lecturer and assistant professor in physics at the Indian Institute of Technology, Guwahati during 2003 to 2007. Then in the year 2007, he joined to School of Chemical and Processing Engineering, University of Leeds, as senior research fellow and project manager. And since March 2013, he is in the chair of functional materials at University of Leeds. He is currently leading the research group, applied photon science, and is also the deputy director of, research and innovation at Leeds University. And he is now actively doing research in functional materials, and his research interest is novel glass laser materials, photonic integration with the dissimilar materials, glass thin films, pulse laser processing and processing of materials, sol-gel processing, laser spectroscopy, and ion exchange with emphasis on applications in biochemical sensors, photonic components, engineering, and energy applications. His current focus is on the ultrafast laser manufacturing of novel functional materials for this application. And also he is doing research in some biosciences and biophysics. And recently in British BBC, there was a news about him, about his new invention on some glucometer-like invention by some particular technique. I think he also will discuss about that particular during this particular webinar. And now these are the some very short about his career. And he's a very active researcher, and many people are doing research under him now. And in these words, I invite Professor Jim Jose to his presentation. And also I think he will give some introduction about his research at Leeds, and also his experience there, and he will share his experience with that to us during his seminar before starting his webinar, I think. Okay, with these words, I invite Professor Jim Jose for his presentation. Thank you, Professor Jim Jose. Yeah, okay, please.
Thank you, Professor Pradyumnan, and thank you, Professor Vinod Kumar, for providing me this opportunity to meet you all and discuss my research. I've been a student at MSc student at Calicut Victoria College. So that time, I think I visited Calicut University a few times. It's long ago. So it's great to see you and to share my research and research experience here. Shall we? How many more minutes I got? Sorry for
Yeah.
being late.
Anyway, 1 hour is our time actually. 1 hour.
Have we still got 1 hour? I
1 hour.
wasted
Okay, you can.
some of your time. Okay.
1 hour.
Okay. Sorry for keeping you waiting. I've had some problems with my computer, and I was trying to restart and start again. Hope everything will go well now. So let me start. Okay. Let me share my screen and see if it works. You see now?
No. You are present. You are not presenting.
You have to give present now.
Present now. Then you open. Yeah. Okay.
Okay, it is coming.
Okay.
So can everybody see now? Yeah.
It is coming.
Okay. Just a moment. So let me start. I was trying to keep my chat window on the side of it.
The slide is not.
Yeah, it is saying presenting, but it does not come. Yeah,
You may select present entire screen.
Is it showing the entire screen? No.
No, it is
Yeah.
stop presenting and again present now and select the particular window.
Let me check.
No, select particular video may not work because when it's difficult to do it in screen.
Okay.
Oh, okay. I tried that, and I think that's what the problem was. Let me see.
Please select the entire screen option after presenting now.
Okay.
Open your slide first, then.
There may be too many screens.
Yeah. Only take one screen.
Okay, let me close other screens then.
Okay.
I think that option is not working.
Yeah, you please open your slide initially, then
Yeah, but present now is not activated.
activated. You present now.
Present now.
So now. Bottom right side of your computer, present now is there. You just click it.
Yeah. I'm trying
Okay,
that.
it's coming. Yeah. Go for full screen.
Yeah, go for full screen F5 or
Yeah, there is a
F5. You put F5. Okay.
yeah, view.
Okay, that's good.
Okay, thank you. No,
You view full screen.
full screen.
And if I do the presentation mode, whether it will work.
Yeah, present. Okay, if F5, you please put the F5. It's not coming.
Is it okay now? No.
No, now it is not clear.
Okay.
F5.
Yes, just a moment.
Bottom full screen is there. You just put bottom full screen. That signal is there. Yeah, right to that.
I mean,
No, right. Right.
Let him go to slideshow. That also will work. Slideshow.
Does it work? No.
No, it is not working.
Let me do one thing. Let me put it in the slideshow and then share it. It's very strange.
Not view. Please select the slideshow option. Just a second left from
Is
the
that
view
one?
button.
That is not
That-
working. Yeah, it is not
That's
working.
not working. I tried a few times now.
You just try again and then F5. Why don't F5 is not working?
Which one is
F5.
F5? Okay, let me
F5. F5 of your keyboard.
F5 or F11.
F5.
Gosh. It's very easy.
Presentation mode, then F5. No.
Otherwise, let him send the copy to you and you may make the presentation.
Yeah, this
Internet.
works.
It is there. Yeah.
That's going into Skype now.
No, not Skype. Okay. Here on top is the locking. I don't know. It is not working.
Okay. Can you send it as an attachment Google Drive or email?
Yeah, just
Some Skype control.
this is not working, you said.
This is not working. I don't know.
Yeah.
So let him please send the copy to either Pradyumnan or Vinod so that you can make the presentations.
Yeah, please send it to the email so that we can get it.
Yeah.
Yeah.
Okay.
Same email will work.
PPT, please share. Yes.
Let me get my emails now. Yeah. I'll email you, Pradyumna. I don't know what's going on. Sorry.
Which email ID? Yeah. Okay.
It's quite a big file, so I'm not sure.
Yeah, of course, it will take some time.
How big? Otherwise, if it is mail cannot take it, you have to put it in the Google Drive.
Yeah, it's still attaching.
And share.
Is it attaching?
Yeah.
PDF format?
Yeah, it's not sent it yet. So, but I don't understand why this is not working. It's bit.
Okay.
In time, you can make it into PDF format. Then it will be easy for attaching.
No, but easier way is to share with the Google Drive so that there is size is not a problem.
Okay.
Yeah, I just sharing it as a Google Drive, I think. Yeah. Me try in the meanwhile. Why is it?
Okay, just
Sometimes there is another option. You just keep the presentation file open and leave the meet, then join again. Sometimes
Yeah, try again. I just may work now. Let's try.
Okay.
No, it's okay.
Fine now.
Oh, sorry. Again, a lot of disruptions. Yeah. So can you see all all okay
Yes.
now? Yeah.
yes.
Okay.
Okay.
Yeah. Okay. Yeah. Sorry again for that glitch.
Yeah.
Okay. Let me start. So okay. Essentially, what I want to discuss today is some basics about photonics and some of our research which is going on in my research group. So quickly moving on to my presentation. So I'm based at the University of Leeds, which is a kind of middle of the island, the United Kingdom island. So it's based in the city of Leeds. So you can see in the slide where we are, which is a kind of middle of the country. So it's a large university with around 30,000 students. So one of our major activities is in the research and its innovation. And there are a number of spin-out companies formed out of Leeds over the last few years, and been quite successful with that. So yeah, I'm based at the School of Chemical and Process Engineering, and we have a research group called Applied Photon Science, and we work on different aspects of light-based research in this research group. We're starting from X-rays to long infrared wavelength lights. So I understand there are a number of students who are from MSc and other backgrounds. So I'll be starting from very basics of optics, light, and lasers, which we call together in terms of application and everything, called as the photonics. So if you have any questions, and you can use your chat window to interact with me during the time. So I'll give you starting from very basics, and let's see where we are going. Okay. So a quick review of what is light. So we know these different forms of light, starting from the sun, the candle, and to the Edison's light bulb, and lasers and LEDs. They all use certain types of materials as a core to its light producing capability. And there are some questions I have put it for the students essentially, so you can just keep interacting with me on that. So you can answer those questions. Like, what light consists of particles and waves? And this is something we know. Or light consists of waves or particles. So that's very interesting. So we have we can start from where light is produced. So we can look back into the structure of an atom. So that is where fundamentally where is the light coming from, or what we call the photons coming from. So if you take a single atom, then you know that we have the electronic energy levels where the electrons are occupied in different orbitals. And when you excite an electron from one of the lower orbitals by giving an energy in the form of light or a quanta, it excites into a higher energy level, and when it relaxes, it emits photons. So I'm going through these slides very quickly. So this is we know that it's a Bohr atom and energy packets. So it is because of the discrete energy levels within the atoms that enable us to create the photons of a particular frequency or energy. And so in terms of emitted photon, it depends on what is the energy of the excited photon. What is the photon or light be incident or imprinted on a material or an atom or a molecule. That leads to that supports the particular frequency of light we want to produce from that. So in terms of the electromagnetic spectrum, it covers a long range of frequencies or wavelengths that we know. Most of us have gone through it. And it starts from the very basic, very low wavelength range, from the gamma rays to X-rays to hard X-rays. If you look at it, there's a very short range, what we call the visible light, which is around 300 to 700 nanometer. And you know, so it's basically essentially all of the spectrum is used for different applications in different ways. And what here we represent here is that what each you know, how does it compare with the size of an object? You know, the different frequencies or the wavelengths of radiation which can be produced. So it starts from very basic, like atomic nucleus, where it compares with where its gamma rays are produced, and it gives an idea about the range of it is. And you can see there's a small range where we use it for mobile frequencies. You know, it's like 300 megahertz to now it is more than 3 gigahertz. It's gone up to around 30 gigahertz. So that's why we're adding new bands into the. So we are using this part of the spectrum for our mobile communication. And further, we look at these are used in several application areas. So starting from the radio spectrum, we use for the radios and mobile phones, and the microwave oven, for example, have a particular frequency that we use. And for in the terahertz region, that is another range of frequencies become important in the last 20-25 years. Or we started studying more about that region, and it's been now used in screening in airports, and also they are used for the imaging of biological objects, like here shown is like a teeth, I think. And we have the infrared, ultraviolet. They are used in different areas, and you got the X-rays and then the gamma rays. The X-rays mostly for medical applications, as well as material science to study materials as well. So there are a few questions here. You can look at it. So we are observing 2 stars in the sky. One is red and one is blue. Which one of these stars is hotter in temperature? You can answer. You can use your chat window, yeah, or you can use some Google search to find out. Don't do that. Okay. So microwave oven operates at 2.4 gigahertz. Why? Why is that particular frequency is used in microwave oven? So this is broadly to give an understanding of radiation or electromagnetic spectrum and its different application areas, and then to kind of get into what we are looking at. So when I say light, we call this entire spectrum, okay, whether visible or invisible sometimes, okay. So it's just it's a common spectrum that I'm referring to here. So So we also know about optics. So optics refers to the behavior of electromagnetic radiation and to apparatus used to study and control it. It's basically, optics is the tools that we use to manipulate light, either focus it or expand it, or to so it's or reflect it, say for example using mirror. So these are the components that we usually call the optics. And the optical devices rely on the interaction of electromagnetic waves with the matter. So when we say matter, for example, if you have a piece of glass, and if you send a light in through that glass, there are different or radiation through that glass. There are different ways. There are different interactions that are taking place with the light and the matter. So that include the reflection of light, and within the material it can get absorbed, and part of it get transmitted. So this is interesting. So that means that we can use light to study material as well, the properties of the material, and that's what we broadly call the spectroscopy. But we do it in spectroscopic studies. Another interesting property of the light that we use, and that in fact helped me to communicate with you. We are several kilometers apart. So this is using the total internal reflection. So we know what is reflection. That's a reflection caused by and we probably have studied the Snell's law and so on, and the Snell's law of reflection and refraction. So this is what is essentially the basic understanding of how light is being confined within a glass and a glass optical fiber. And so what we call is the total internal reflection, where the light is reflected back and forth within the glass fiber, which allow us to send signals to the optical fiber across the globe. You can see that the optical fibers are connecting us between the different continents. And for internet data, video, when we make phone calls and all, the signal is actually going through somewhere through this fiber, not always through the electromagnetic radiations through the air. So in some places it's going to the satellite, coming back to the earth, and then uses the optical fibers. So in summary, a quick review of light, optics, and another aspect is laser. So this is, we know the definition, but essentially what it is a simple version is like you're trying to amplify the light within an oscillating cavity. So we use a light producing material in the middle, what we call the amplifying medium, and then we use two mirrors to basically confine the light within this, and then to oscillate the radiation within the cavity, within this optical cavity, and at certain point it comes out with a higher intensity or brightness. And that's basically what we call the amplified light, which we call it the laser. So these are all different types of sources, and the laser sources are different from normal light sources that also you probably are aware of. So I'm not getting into that. So just to give a quick overlook, what is photonics involved? So it involves light, study of light, generation of light, and the components, the optics, and that means basically manipulation of light, using light for different, using light in different ways, and amplification of light as well. So that's where in producing different types of lasers and use of those lasers in different applications as well. So it's very broad now of what the photonics covers. So that's briefly the introduction, and then we move on to the second part of my talk, which is basically the research that's going on in my research group, which involved what we call the photonic materials and devices research. So moving on to the next slide, in terms of materials, so I kind of very quickly mentioned that the materials can produce light when we have electronic transitions, for example, in atoms and ions. Or it could be some more transitions in molecules, depending on, say, for example, dyes or other types of molecules. So in my research group, most of the activities based around glasses and thin films and oxide thin films. So in terms of what is producing lights, essentially using these elements in this lanthanide series in the periodic table, what you can see is at the bottom you have two rows in which the top one, what we call the lanthanides or the rare earth elements. So here are some examples in which these elements are incorporated into glass and then producing different types of different colors or being used in, say for example, this is a thulium doped glass which is producing blue light under laser excitation, and this is again an erbium doped glass which is producing green as well, and this is an optical fiber which is producing green light. Also this produces infrared and other lights. So these different rare earth elements, when they are in the ionic form, they can emit light at a specific frequencies. This is essentially coming from their electronic level, which is based in where the electrons, unfilled electrons, are in the 4s shell or 4s orbital. So so these in the at the bottom you can see that we can incorporate these ions into say for example nanoparticles, which are shown here, very small particles which are of the order of 10 nanometer up to 50 nanometer for example, and they can be produced in different shapes, sizes, and then we can use those nanoparticles, light emitting nanoparticles, to say for example imaging tissues and biological materials. So that's some example shown at the other end, which is producing green emission. So these types of materials are produced and tested in my laboratory for different applications. So in broadly, the advantage with these rare earth ions are, you can see that they can produce light from, say, for example, 300 nanometer up to 5,000, around 5,000 nanometer. But it all depends on where these ions are placed. Say, for example, it's a particular type of glass or a particular type of crystal. So it depending on the local environment as well. Some of these emissions are radiative, some of these are non-radiative, means it won't produce light which we can see. So it's converted simply into optical phone, into a phonon and convert into heat. So you cannot get the useful radiation. So in terms of these ions, they are already being used in a number of, you probably be seeing if you have an LED light bulb in your room, it contains one of these rare earth element in it. And they are very important, and we know that we've got some places in Kerala where we can get these elements. So it's very, say for example, the sand from the Alleppey district has been used to produce these elements together with other radioactive elements. And there was this company called Indian Rare Earths based in Chawra, which was used to produce it. I think it's KMRL now doing it. So we have sources of these ions or elements within in our state as well, and these are very important for the technology for the future. And so this is major producer of these elements are China, so they have the monopoly over it. So it is very important that we make use of these natural resources in an efficient and productive way, which helps our state as well. It's important. It's a very important, technologically important element. These elements are also used not just for the optical fibers, which are in the optical fibers, which I'll be discussing now. They are also used in producing magnets, which are important for the non-conventional energy sources from, say, for example, for the wind turbines, where you need to make these big magnets. One of these elements called neodymium is used. Okay, getting back into my research, so in terms of photonic integration, so we probably have been introduced into electronic integration in your studies. So it involves integrating different electronic components on a chip, on a silicon chip. So in photonic integration, there are different approaches are tried. One of them is integrating photonic components onto silicon chip. So the idea is then there are certain functionalities where the electronics is probably not fast enough. where the light could provide an advantage in terms of speed and efficiency. And also the electronic integration is kind of reaching its limit, because we cannot go any beyond in terms of how small a component can be produced on a silicon chip. So it's almost at the level of 20 nanometers, almost getting to the level of an atom. So, one of the ideas is to create a kind of a composite chip in which we have layers of electronic components on which you integrate some of the photonic components. The photonic components, certain aspects are important. One of which is an amplifier. So the silicon is an indirect bandgap material, and it's not an ideal material to produce a laser in terms of exciting the element, or in terms of using it to produce a laser. And also it is not suitable as a material to amplify light directly. So if you look at some of our, say, optical communication link, so say, for example, we use data, your computer, video, voice, we use the internet. So the signal is sent through optical fiber at some point, and within the optical fiber, the signal might get attenuated or reduce its strength or length. So then you have to amplify it. So you need an amplifier in between to amplify the signal for the long distance transmission. So it is similar to the function of electronic amplifier, but can we do the amplification in the optical domain? So that's what we call one of the components used is called the erbium doped fiber amplifier. It is simply what is involved is a glass fiber. Glass, I mean, is a silica based glass fiber, and the glass fiber containing some of these, one of these ions called erbium, which is in the lanthanide group I have just mentioned. And the advantage with the erbium is that the erbium has got a light emitting property, which is based at the highlighted here at the 15 nanometer wavelength range. So if you excite these erbium ions into this level, for example, then it can non-negatively decay, and then it can produce light at the 15 nanometer wavelength range. So this particular wavelength range is of very interesting, because that wavelength range is where the silica optical fiber has got the minimum loss. So we are using this particular wavelength range in the silica optical fiber now for communication. So essentially in this box of fiber amplifier, what we have is a fiber of erbium doped fiber, which is around 10 meters long, which is coiled inside. And why we need very long fiber? Because we cannot dope this fiber or incorporate the fiber with a lot of erbium, because it is depending on the, so if you look at simply one erbium ion can emit one photon. Yeah. So if you want to produce more and more photons, you have to incorporate more and more erbium ions into it. So that means the silica as a material cannot incorporate that very high concentrations of erbium, or it cannot uniformly distribute those ions within the silica network. So when we say silica network, what you have is, say, for example, silicon and oxygen. Yeah, it's a simple glass, if you can say. And if you try to incorporate erbium into it, it'll go into the network, but it cannot go beyond certain concentration. For example, if you here you can see that when you try to put more and more erbium ions into the glass, it starts clustering. It's like if you're making a cake, and if you put too much raisins into it, it may not distribute. It will end up at the bottom. Yeah, it just clusters together. So it's about how well you can distribute within the material. If you can distribute these ions very well, then you can get a very good amplifier in a short length. So that's where what we call a waveguide amplifier coming in. So here what we have is, for example, a glass at the bottom with a refractive index N1, and you modify the surface of the glass with a refractive index slightly more than that is called N2. So now if you send the light from one end of this layer, the light will be confined here in this plane. But if you want to confine the light in, say, one dimension, then we had to create a channel waveguide like that on the right-hand side. So in the channel waveguide, if you incorporate the erbium ions in a very high concentrations, so we can get similar kind of amplification or optical gain, which we can use for amplifying signals in an optical fiber network. So this is what we have tried in our laboratories to create very high concentrations of ions within the silica material without them being clustered within that. So the technology that we use, which consists of a high power laser, in a sense, is what we call the ultra fast laser or ultra short pulse laser. So this particular laser which basically sends pulses of light, where the pulses of duration is very, very, very small, which is of the order of, say, what we call 45 to 100 femtosecond. Though the energy per pulse is low, what we have is a lot of photons contained within that very short pulse of light, and which allow us to confine, produce materials to ablate from the surface or evaporate from the surface and then deposit onto a substrate, what you call here. So you can have a substrate here, and then you ablate the surface with this laser or target material, and then you produce a layer of waveguide, as we have shown in the previous picture. Sorry that I'm speeding a bit. So if you have any questions, you just message me. So I'll answer you at the end. Okay. So you can see an example here. So this is the surface of a target material. So this is a source of material that we use for the erbium. And then this is by using different laser energy per unit area at the surface. So you can see, depending on the laser energy per unit area, it ablates the surface in different ways. It's like using different drills to drill a material. So depends on the strength, and sometimes not just the strength. It's the rotation speed of the drill and so on. It produces it attacks the material in different ways. So anyway, here what we trying to do is to create a uniform ablation. So you get the material coming out is mostly uniform. So this is what we call the plasma. So we call it plasma. This is not quite a fully ionized material. So it's when you use this particular type of laser, what we call the ultrafast laser, it is producing a plasma which contains only around 5% ions. The rest of it is kind of nanoparticles. So the advantage with this is kind of a physical ablation of material. So the advantage with this is that you can virtually, you can use any target material, and these lasers produce sufficient energy per unit area to ablate it, or evaporate it from the surface in a layway. So we first study these target material properties so that we can control the ablation properties, and then we move on to depositing it onto a substrate, and basically through a thermally assisted diffusion process, you get these ions diffused into the surface. So kind of a graphical representation, if you can see. So what we do here is, we got the laser incident on, the plasma is produced, the plasma interacts with the surface of the substrate, and then you have that modifies the surface. So you have a new type of glass. It's still glass, it's a silica-based glass, and it's modified into a doped glass, where the dopants are coming from the target. So you grow it subsequently with the different layers. So this is something we kind of developed at Leeds, and being used in different application areas. So on the right, you can see that you can use a mask so that you only modify certain areas on the surface. So this is aiming at producing different types of photonic components, essentially amplifier or light emitting components integrated onto the surface of a glass. So this is like a cross section of that surface of the glass. So what is happening inside? So what we do here is we take a slice from the surface of the glass, and then you can look it into an electron microscope and see what is happened. So the image on the on your left, basically, I hope it's showing in the same way. So what I have shown implanted is basically that is the layer of glass which is being modified by this process, and which contains all the elements from the target glass, and we can control what is to be incorporated into there. So creating an homogeneous layer, very high doping concentration comparing to, so if you want to create an amplifier comparable to the performance of an erbium fiber amplifier, which is using a 10-meter long fiber, we basically have to incorporate the same amount of or similar amount of erbium ions into a very short length. If it is 1 centimeter, that means to get the same kind of gain, optical gain or amplification, you have to use the same around the same concentration of or we had to use a very high, same number of erbium ions, which means very high concentration in a very short length of about 1 centimeter. So here we are showing the different elements in that layer, which can be analyzed using, again, TEM, transmission electron microscopy. This is a close image of what is shown here. It's again that the doped region, which is modified using this laser process, which I described. And again, some of the important thing is that you can see a step change of the elemental concentration at the point where it is stopping. So this is kind of giving a kind of a refractive index increase about this, what you call a step index change, step change in the refractive index, which is interesting comparing to many other techniques which produces different types of refractive index modification. We can do the same process on a silica layer on a silicon, which is interesting again for the context of silicon photonics application side. So this is process we applied on a silica on silicon, and this is an example here. So you can do the implantation, you can control how deep you want to go, and control the thickness of the layer you can produce. So essentially, it incorporates a doping within the layer. And here we do some of the characterizations of the material. So one thing we want to know is the refractive index change produced by the material. So here you can see that the refractive index is about 1.62 at the surface, and the original refractive index was around 1.45. So it is around 10% increase in the refractive index. So in terms of the light confinement within an optically guiding region, it is the change in refractive index which determines how thick the layer you need. So if the change in refractive index is very small, you need a very thick layer, and you need a larger waveguide to confine the light within that region. So if you can produce a high change in the refractive index, that means you can make a smaller waveguide which can get light through it. Okay. Again, I'm not going into the details of that. And here this work demonstrates that we can control the doping concentration, we can control the optical properties in that way. So here it is shown the emission spectrum of this doped layer. So the black spectrum is one, that of the modified silica glass that I am talking about here. So it is typically that is the wavelength range in which the optical amplifiers are used for the communication purpose, fiber optic communication purpose. So this is again showing the different ways of controlling. So we can use the laser energy, change the laser energy, and we can control the growth rate of growth of the layer as well, and to certain limits. It's of course limited by the material properties. Okay, when I talk about it, we can put different ions like thulium, erbium into the film, and then produce the optical properties for different other applications. For example, in this case, with the thulium, you can go up to 200 nanometer. So if you dope it with erbium and thulium, you can go from around 1400 nanometer up to 2000 nanometer. So this is also important because the erbium has got a limited bandwidth, and searchers are trying to extend that bandwidth to the longer wavelength and shorter wavelength. So the optical fiber can support those wavelengths, but there are not good amplifiers in those wavelength ranges still. So they're to be commonly applied or deployed. Okay, so this is another thing. Once you have a doped layer on the surface of the silica, we can also create, say, for example, a ring like this. So this is using focused ion beam. We created this ring. So you can see that there is light coupled from an optical fiber here into this ring. So this is a very small ring. It's around 50 to 100 micron size. And you can see that what you call the light coupling into a ring, which is called again something called the whispering gallery mode. So this is, you can produce a very small laser with this kind of discs or rings on the surface of the glass, but it requires a very precise manufacturing. So it still requires a lot of, especially this type of material. You need a very precise roughness, means smoothness of the surface and smoothness of the edges. These are all very important. So in total, so we can produce a waveguide amplifier, for example, what is shown here in the red, on a surface of a glass, especially on the silica glass, and we can also, produce it into splitters. So we can create amplifier splitter together on a surface. So these are very important when you have, for example, the fiber is coming to home. You have to split at some point so that it goes to the different homes. But when you split the signal into different fibers, you essentially have a loss of signal. So you need to amplify it. So one way to do is you amplify it and then split it so that all homes will get the same, signal strength. These are some of the researches going on in terms of developing this into a commercial product in terms of an amplifier splitter together. So the project is part of a collaboration with the different universities, and so we do this work on a fiber as well. So you can see here there is a waveguide, a small waveguide with a green emission on the right-hand corner. So that's coupling light into the waveguide. So when the erbium ions, I have mentioned that the amplification is in the infrared. It's in around the 1500 nanometer wavelength range. But you can see that green, which is produced by a process called upconversion in the material. So it's like when two simultaneous photons or two photons are absorbed simultaneously, or then basically it excites to a higher energy level and produces shorter wavelength radiations, or higher energy radiations. So what you call the upconversion in this material. So this is the upconversion process is used in the imaging research, which I kind of briefly described in the nanoparticle aspect. Going to the non-invasive biosensing research still going on. So one way we looked at how these materials can be used at applications in sensing. So the advantage here is you can control a doping concentration on the surface and doping thickness and some other aspects of the properties of this material using this process, which we try to use to measure glucose through the skin. So why glucose measurement is important? As we know that the diabetes is a growing problem around the globe, and there are different types of diabetes. In particular, the type 1 diabetes, people with the type 1 diabetes, they need to check their glucose level several times a day, and then to control their insulin injection. So that means you take the blood from the different fingertips and measure it. So if you are measuring 5-6 times a day, basically, pricking the finger several times, it's quite painful. So there was a lot of research going on producing different types of non-invasive glucose sensing. It's not a new idea. It is being tried with the different technologies, still not very successful. Even our case also, we are still in the development process because it has to go through a lot of testing and trialing process. So though the diabetes in itself is not the disease, it actually creates other complications, which is why diabetes is more a problem. It affects the heart, the eyes, kidney, feet, when it's and liver, and creates, making what you call the comorbidity is much more difficult to survive. To control, basically. So it's a huge growing problem. It's increasing, ever increasing. I'm not going through these slides. It's going through it quickly. So you can see that the countries which have the dark colors, basically India is one of them, China, US. So we have more than 20 million, in our countries. And if you look at the other side as well, we got around 9 to 12%, and it's ever growing of the population, and 12% of the population have got diabetes. That means around 10 in 100 people in India. So it's the same around the globe. It's a growing problem. At the moment, there aren't a permanent cure for it. So one way to do is to control the glucose levels or the sugar levels in the blood. So in order to control it, we need to monitor it or measure it. What is the actual concentration of sugar, and then accordingly had to use the insulin, or you had to use you had to have food containing glucose to manage the glucose concentrations. So there are no painless glucometers on the market. There are some kind of called, not fully non-invasive ones, but long-term ones. So our idea was to use this kind of the glass materials which I have shown before for this application, and something which can be used, for example, like something wearable or something which we can use the finger to measure it. So that was the idea. So the concept here is to use some of the glucose optical properties. The glucose have got an absorption around, say, 1500 nanometer, where the erbium also got an emission spectrum. So can we exploit this property of the doping within the glass to use to measure the concentration through the skin? Since it's a non-contact measurement, so we have to have basically the photons to interact with the glucose in blood or under the skin by some mechanism. So there are short range interactions, and then we have to have some long range interactions so that we can measure it from the deep levels within the skin. So we are using we are exploiting some of the quantum principles. One approach is using, say, a simple description is probably, if you have, through the electrodynamics in MSc, you probably have studied the method of images. So this is using similar kind of method of images in photons to measure it. So basically, we use a doped glass which contains the probe ions, and then monitor the probe ions. So the implanted layer here contains some of the probe ions, and see how the properties of that ions change. In particular, the light emitting property or the decaying property of that ions, and then use it and monitor it to measure the concentration of the glucose through the skin. So it's still a process. So this is kind of a first prototype we produced, and we did some initial clinical trials, very early stage clinical trials. I would say there's a lot to go. There are a lot of testing procedures and statistical analysis and all this to be carried out in order to get a biosensor product into the market. So we are still in the process of improving the sensing ability of the material itself. The material means a simple doped material won't be sufficient, so we need to add other additional functionalities. We are also using the same material processing technique for other applications. For example, strengthening the glass surface. So the glass is weak because you got these small defects on the surface. And the current technique is what we call the glass used in mobile phones. So even though we call it gorilla glass, if you drop it, it will break most likely. There is a likely chance of it get broken. So the glass breaks essentially because you got these micro cracks, and the technique currently used is called ion exchange to heal, or it's basically to squeeze these gaps so that it won't easily break. This is the current technique used in the Gorilla Glass. What we're trying to do is we have to actually heal the surface so that it completely seals off these defects, so that the glass can be stronger than it's not a normal glass which can be used for mobile screens and so on. So that is a quick overview of some of the research. Thank you for these are my funds research in the UK. And this is my team. It's not complete. There are some new researchers in here. Some of them are finished and moved on. So thank you very much.
Okay, thank you, Professor Jinjos, for very exciting and enlightening talk. Any questions from audience? Questions from attending students and teachers? Actually, his talk is mainly based on optics and also laser reactions and material science, materials preparation, and rare earth, importance of rare earth elements in glass-like materials, and how its optical properties modifying by the introduction of rare earth elements. And femtosecond lasers also he mentioned about using some thulium and erbium, etc. Any doubts in this regard, please?
All are tired.
All are tired? Okay.
No, I mean, see, it's very, very strange, isn't it? You don't see each other quite. So I don't know that I can't see your faces and what's happening when I am talking. So that's
After lunch. After lunch. Okay.
So feel free to ask any questions if you have. I tried to. Yeah, I rushed a bit.
Yeah. Okay. I think. What about the pandemic situation in England now? Your region?
It's getting better. So I mean, getting better means the cases are going up, but people are getting normal. So the schools are open today.
What about universities also open?
University will be opening next week.
Okay.
Not fully, but the research labs will be opening next week. So I just managed to go to the lab yesterday just to see after 6 months.
Oh,
so,
6 months. Okay.
So it's all affected the projects, the PhD students. So yeah, it's so I think it's now people are trying to live with it. So
what about your EPSRC project? It is continuing. Okay. It is.
Yeah, the project is still on. Got a new project on this nanoparticle side. So there'll be issues around investment and things in there. Let us see how things turn around in the coming years. So, have you started teaching there? Or?
No, so far not teaching now in Kerala or in India, I think. We are also okay. Some teachers are only coming, and we are working at home. Actually, online teaching, mainly online teaching. We are also. What about your place? Also, maybe online teaching is there? No.
Online we will be. We've been a bit lucky because we're just starting to teach end of September. So our term starts end of September. Okay. So we had to record lectures and then give it to the students. So and then arrange
online classes like things.
Yeah.
Would like class teaching like things are not there.
Yeah.
Any questions, please? Yeah, Fairoja, you can ask one question.
Yeah. Hi, this is Fairoja, and I am mostly interested on laser-induced structural changes in materials, and I'm doing theory for that. Yeah. So I want to know, it's really interesting talk, and I want to know what is the laser energy you are using for irradiating, and have you ever experienced any other structural phenomena like ablation or something phase changes in materials, etc.? And
Yeah.
how do you control this?
Yeah, so we also did some laser micromachining in the past. So just briefly, the pulse duration that we use is 100 femtosecond and less. And the energy per pulse is around, say, 100 microjoule. And the repetition rate of the laser that we're using is 1 kilohertz and 10 kilohertz. And we have also, so when you ablate the surface, I have shown one surface in one of my slides. So in that case, you don't see any sort of structuring on the surface. But if you try to irradiate on a film, for example, a thin film on a substrate, then you can see the nanostructuring of the materials on the surface. So that's being trying to, people have looked at it for different applications like like light absorption, for example, in solar cells, to produce a kind of a black surface in silicon. So these are all possible with the particular type of laser I'm using, but we haven't looked at, we did one study on the surface structuring and also some micromachining, but haven't done anything beyond that. But it's possible with this laser, yeah.
But it doesn't happen accidentally also?
Oh yeah, accidentally means if you basically focus this laser on a surface, you will accidentally get anything. So so I mean it's very interesting because it's that's why it's so basically if you just focus a femtosecond laser on a thin film on a surface, the patterns are produced.
Yeah.
And then you control the energy, and if you control the wavelength also, I think you can control the periodicity of the dimension of the structures you can produce, the morphology of the structures you can produce as well. Yeah. So
nanocrystals we can produce on the surface. Yeah. Okay. Nanocrystals.
Yeah. In my case, what I'm doing is I'm not interested in that structure on the surface. So we're ablating the material. So you're producing this material, I mean, ablating the materials off the surface and then depositing onto another surface and then allowing it to diffuse into that second surface where you modify the substrate. So in that case, we're not really bothered about what's happening on the target where you ablate from. But there'll be structures produced in there depending on the energy, the focusing conditions. It's very important. Yeah.
Do you have any future plan to look into the structural dynamics?
Yeah, we can do that. I mean, it's doable. I mean, the laser we have is capable of doing it. It's somebody is interested in those aspects is getting on with it. So.
Thank you.
So if you are interested, we can discuss and see.
Yeah, we can discuss. Yeah. I'm mainly interested in structural dynamics, and I look in the aspects of phonons, and I work on electron phonon and phonon coupling mainly, magnetic materials and normal materials also.
Yeah. See this ablation dynamics itself. When you focus a laser at the surface of a target material, how the material is being ablated.
Yes.
There is a lot of conflicting and theories around it. What you call the Coulomb interaction, and which is probably the most commonly accepted. So, and again, it's what we observed is like it's not fully plasma. So when you say Coulomb explosion, it should be a plasma. I mean, basically ions coming out. But in our case, it's mostly nanoparticles because it's more like you're drilling a material and you're producing materials of a very small dimension. So it is very less amount of ions. Probably 95% of it is particles. So that's still an interesting area. I mean, especially it's more complex when you ablate glasses or multi-component materials. Most of the studies are around ablating metals because they have kind of one type of element in it, and the study becomes easier.
Yeah, I have done a study on that. There are many possibilities like ablation. Not
Yeah.
only that, there are incoherent like phonon-phonon coupling that will make into thermal melting and many non-thermal and thermal meltings, etc. Yeah, there are many possibilities.
Yeah. I think we are not experts on that side, but I think the laser can do it. We can, we got some diagnostics tools in the equipment we still haven't used. One is called Langmuir Prof. So this is look at measuring the energy of the ions. And we have also plans to do some optical emission spectroscopy. So we can look into the plasma and can we understand better, what's going on at the point of interaction. Yeah.
Oh, great. Yeah, thank you.
No problem. Thank you.
Yeah.
Any other questions, please? No, any other questions? I have a question, because what type of collaboration we can make between you and with our
So
university?
there is there is this student exchange program now too. I think that's something we can look at. So where the PhD students can spend some time here. I think it was previously for Inspire Fellowship students. There is an opportunity to spend 6 months in the UK, things like that. So what I can do is whenever there is a kind of any kind of collaboration projects funding with the India, we can share with you guys and look at it. Yeah.
Okay. No more questions? Yeah.
Yeah. So you got PhD students listening to this, or it's sorry, MSc students?
MSc students are there. Any are there?
Okay.
Yeah. Anything to tell them?
Do you have a photonics or photonics course in or?
Photonics separate course. Photonics is not here.
No, I mean.
Material science special paper is there. No,
Okay.
photonic special papers. Material science only. We have
Spectroscopy also, or do you?
of course.
Yeah. Okay. Yeah, when we studied, it wasn't there. Yeah. I think the closest was the electrodynamics. Yeah.
Yeah.
And solid state physics. Yeah.
Syllabus are the same almost.
Yeah.
Okay, no more questions.
Hello.
Yeah.
I was a bit late today.
Yeah.
I would like to know, where did you complete your MSc and your course in Kerala?
So I did my MSc at Victoria College, Calicut.
Yeah. Which year, sir?
Victoria College. Victoria
in
College.
which year? Which year?
It was in 1995, 96.
Okay.
Yeah, I finished in 95, and I've been around in Victoria 96, doing a lot of teaching around. Yeah, before starting my PhD, and then I started my PhD. I mean, did my PhD from Mahatma University.
Yeah.
Where Pradyumnan was also there. Yeah.
Yeah. Okay, thank you, sir.
No problem. Thank you.
Okay, then one more question. Vinod, sir, any?
No questions. You can wind up probably then.
Okay, then I think very happy to be here, because you know that Professor Jim Jones, who done very good work at Leeds, and he also told you about that particular invention, about that particular sensor, glucometer, and that is under I think under more studies, and not in market, I think. No, is it?
No, not yet. No. I've been asked by so many people. I cannot come to India now, so they will ask for to commit.
Okay.
Yeah, it's been delayed because of issues around some funding, and so that is affected some of technical development. So we currently have a team. I work with the quantum optics group in physics, and also the bioscience in the medicine and health. So we're still working on it. So hope it will get into market sometime. But it seems to be a long journey than I thought. Yeah.
Okay, we know that because now everyone is using syringes and other thing for checking their bloods. Yeah, putting some cracks on their skins. Then only they can do that. So without that, it is good. Okay, then thank you very much, Professor Jim Jos. And on behalf of all of you from the Department of Physics, University of Calicut, we are very thankful to you for this particular presentation or sharing your experience at Leeds and the research experience, and also your magnanimity for collaboration with us. Thank you. Okay, thank you all.
Thank you.
Okay.
Thank you.
And see you today's